Hi, my name is Adlesick, and this is Lab 1, Constant Velocity for Physics 2211. Let's start out with an introduction of our lab. The purpose of this lab is to investigate the motion of an object moving at a constant velocity. Our object for the sake of this experiment was an expo marker, which can also be identified as our system. To define some key terms, a system is the isolated object under observation, and the surroundings are the rest of the universe. Physics is basically studying the relationship between the two. Net force is the vector sum of forces acting on a system by its surroundings. Moving at a constant velocity means that an object, in this case a marker, is moving at the same speed without changing direction. A couple important fundamental physical principles we draw upon in this lab include Newton's first and second laws. Newton's first law states that if a body is at rest or moving at a constant speed in a straight line, it will remain at rest or keep moving in a straight line at constant speed until it is acted upon by a force. Newton's second law, also known as the momentum principle, states that the acceleration of an object is dependent upon the net force acting upon the object and the object's mass. Here are two important equations that we will be implementing into our code. The first is final position equals initial position plus average velocity times the change in time, or delta t. The second is final velocity equals initial velocity plus net force divided by mass times the change in time. Now let's take a look at some models in play to help us visualize the physical concepts of this lab. These free body diagrams allow us to see the forces acting on our marker in two different situations. The left scenario being the marker moving with constant velocity and net force equal to 0, and the right one where the marker is not moving with constant velocity and net force is not equal to 0. Gravitational force and normal force act upon the marker in both scenarios. These forces cancel out. The marker without constant velocity has a third force acting upon it, however, and this additional force vector, whether it be frictional force, applied force, or whatever else, does not cancel out with anything. Now time to dive into our experiment. The actual experimental procedure of this lab is pretty straightforward. Our system is the expo marker, and our surroundings are everything else. As you can see in the setup, the expo marker moves along a meter stick to the left, and we record a video of it doing this. We import it into Tracker to plot the position versus time graph. Then we create a computational model of our predicted values in GlowScript. A key assumption we must make is that the net force on the marker is 0. Here's a video of the moving expo marker in Tracker. I set the origin at the initial position of the marker, with the right direction being positive and the left being negative. Thus, as the ball moves from right to left, we obtain a position versus time graph with a negative slope. Now on to the computational model. Using the guidelines of the starter code, I edited the code to represent my data and constructed a computational model which plots the predicted position versus time of the marker. For a deeper look into my code, I changed the initial marker position to be the vector 0, 0, 0, since I had set my origin on Tracker to the end of the meter stick where we started rolling the marker. Thinking about it, it makes sense that the ball would have 0 displacement if no time has passed. It has not moved yet at time 0. I set t equal to 0 since we started tracking the data for the experiment at 0 seconds. I made delta t equal to 1 over 28 because there are 28 frames per second in my video. As for marker.vel in the previous slide, I set it equal to negative 0.25600 because negative 0.256 meters per second is the approximate average velocity of the marker over the period from 0.502 seconds to 3.003 seconds. I obtained this average by taking the weighted average of the average velocity for 5 equal subsections of time during our time range. Note that average velocity equals displacement divided by time. Here's our calculation loop that runs while time is less than 3.5 seconds because that is how long our video collected data for. Circled are the two important equations we identified earlier. Here's how the equations correspond to the code. Finally, let's discuss our results and make conclusions on our findings. Here we see a side-by-side comparison of our observed and predicted time versus position graphs. They follow a similar trend line of velocity, but they are not exactly the same. This is because the computational model plotted values for a perfectly constant velocity, whereas the observed values from Tracker, in reality, must account for some sort of frictional force. Time for a little more analysis of our experiment and results by asking some important questions to help us understand the physical concepts of this lab at a deeper level. What if I had flipped the axes when I created my Tracker graph? Originally, I oriented the axes to have left be negative and right be positive. This yielded a downward sloping position versus time graph. If I were to flip the axes, the only change in results would be that the graph would have an upward or positive slope. We would still be able to derive the same conclusions. Our computational model makes the assumption that the net force acting on the marker by the surroundings is equal to 0. Is this really justified? No, the net force is not necessarily equal to 0. We know that friction acts on the marker, causing the marker to slow down as time increases. It is, however, not possible to say how many pushes and pulls are added to give 0 net force in the case that we observed. Should we try to alter our computational model to account for the forces acting on the marker, it may be useful to account for frictional force in our equations.